Hello, and welcome back to another IB Math speedrun with me, Vince. So today we're going to be going over the trigonometric functions, so let's jump right in. So we've already gone over trigonometric equations and identities, but it's also important to memorize the function graphs of trigonometric equations. So, what do they look like is the first question. And the sine graph looks something like this. As you can see, it has a peak over here. This would be, let's use degrees, so this would be 90 degrees. It hits 0 again at 180. It has a trough at 270, and then it zeros again at 360. So, I mean, if you plug in these values, you can see that like over here at 60, this would be equal to root 3 over 2. And then here at 45, this would be root 2 over 2. Then here at 30, this would be 1/2, and so on. Now, next, what does the cosine graph look like? Well, the cosine graph looks a bit like this. We go down here, down there, down here. So you can kind of imagine it as the sine graph shifted to the left by 90 degrees. Remember that cosine 0 is 1, and then cosine 90 is 0, cosine 180 is -1, and so on. Notice that both of these functions have a range between -1 and 1 and a period of 360 degrees. A period means like how often does the function repeat, because if we expand this function this way, this function will repeat like this indefinitely. For both sine, cosine, and also the tangent function, but we'll get to the tangent function later. They will repeat indefinitely, and so this distance here between two successive peaks, or that's what we call a peak, yeah, is 360 degrees or 2 pi. Now, the range of the tangent function is a bit different because the tangent function looks something like this. So let's get the green pen for the tangent function. And the tangent function looks a bit like this. So as you can see, there are a few things immediately different with it. First of all, this green line will continue up indefinitely because as the angle approaches 90 degrees, the tan gets greater and greater. So it will really encompass all real numbers. The second thing is that this tan function actually has a period of only 180 degrees compared to 360 because tan repeats every one cycle, every half rotation, or every 180 degrees. Yeah, and this is because of the symmetrical property of the circle, where 2 points on the diameter represent 2 angles with the same tangent value. And so yeah, that is pretty much it. So I think we can go into some questions now. So the first question is I guess we'll do an even one. So use the graph f of theta. I'm just going to say theta is 0. It's equal to tan theta to deduce the graph and properties of g of theta is equal to cotangent of theta. So what do we know about the graph of tangent of theta? Well, we know it looks something like this. We know it looks like this. And so now we need to deduce the graph of cotangent theta. And so you know cotangent theta is actually equal to 1 over tangent theta. So when cotangent theta is close to 0, we know that, when tangent theta is close to 0, we know that the cotangent must be a large value. So we can make it seem like this, and then similarly, as tangent theta is negative, a negatively large value, cotangent will look like this. So it's sort of like a mirrored version of this graph. So the cotangent graph should look like the blue lines here, compared to the tangent graph, which should look like the green lines. Yeah. So next, we have use transformations of y is equal to sine x to graph each of the following functions. And we have y is equal to sine x plus 3 pi over 2, and dy is equal to 2 sine 4x plus pi minus 1. Okay, so if you remember our unit on function transformations, you'll remember that all of these functions can be expressed in the form y is equal to a times f of f of b times x minus h plus k. So this maps all the function transformations. So in the case where y equals sine x plus 3 pi over 2, this is equivalent to moving the graph left by 3 pi over 2 units. So if we have the original sine graph, here, and remember this is pi over 4, pi over 2, oh sorry, no, this is 2 pi. Oops, what am I doing? This should be pi over 4, pi over 2, this should be pi, this should be 3 pi over 2, this should be 2 pi, and so on. So if we move this graph left by 3 pi over 2 units, it will look something like this. So this blue graph will be our new graph for the first one. Next, y is equal to 2 sine 4x plus pi minus 1. Is that correct? Yeah. So, what we have here is, first of all, where should we start? Let's look at the graph of simply sine 4x plus pi first. So sine 4x plus pi will be shifted to the left by pi degrees. Since when x equals 0, pi will equal 0. So this initial graph will look like, x equals 0 sine, it will be sine of pi. And sine of pi is 1. And since we're multiplying the inside by 4x, well, this is going to compress the graph by 4 times the amount. So what we actually get is something like this. So if we go down, and then, let's see, 4 times the graph, so the original graph would complete this cycle in that space. So we would need to, it would look something like this. So this would be the graph of this first part, but now we multiply it by 2. So this means we actually increase the amplitude by a factor of 2, so that's the original peak. I'll put it over here. So it would look like something like the green line, except that we need to translate it downwards by a vector of 1, since we have minus 1. So our final graph will look something like this. Yeah, something like that. Okay, on to the next one. Final 2 questions. We need to use transformations of y is equal to cosine x to graph each of the following functions. And we need cosine 3x minus 1 and y is equal to 3 times 1 plus cosine 2x. So for this first one, cosine 3x minus 1, well, cosine 3x multiplying x by 3 tells us that we're going to have to compress the function by a factor of 3. So the original cosine graph will look like this. So if we're compressing it by a factor of 3, and then we're also subtracting 1, so that means we have to have a downward translation of 1 unit, then let's think. So if it repeats there, it repeats here. Actually, let's just copy this graph. I can just do this. So downward translation of 1 unit, and we need to, oh, can I not stretch? Is that not a thing? Okay. Well, anyway, we'll just use this for reference. So the original cycle repeats every there. And so we need to make it repeat 3 times faster. So actually, let's just trash that. So what we're really looking at is a graph that repeats, should reach this third peak there. So that's too little. That's too little. 1, 2, 3, yeah. So that it should look something like this. That's the new graph. Yeah. And then finally we have 3 times 1 plus cosine 2x, which is equivalent to 3 plus 3 cosine 2x. So this will be, let's 3 plus 3 cosine 2x. Let's fix our equation. There we go. So 3 means we're, of course, adding 3 to the height. And then 3 over here means we are stretching it vertically by a factor of 3. And then we're squashing it horizontally by a factor of 2. That's a lot to take in. So this is 1. We need to go 2, 3. And then on top of that, it's 3 cosine 2x. So we need to make it repeat twice every time this original graph repeats once. And we need to make this the middle. So it should be, oh dear. Yeah, it should look something like this. So as you can see, every time this red graph, which has just the normal graph, repeats once, we've squashed this graph so it repeats 2 times. Except that we should not be starting from 0. Why did I do that? Should be starting from there. So yeah, that's pretty much it. If you're unsure, let me just quickly get a graphical calculator out and sketch the graph. So we have y is equal to 3 times 1 plus cosine 2x. And so as you can see, let's put the earlier graph, y equals just cosine x, for reference. So as you can see, it repeats twice every 1 time this cosine graph repeats. So like a less ugly version of this. So yeah, that was it. I hope you enjoyed the speedrun, and I hope to see you in the next one.